All right, so whenever we have infinities showing up in our integrals, we get this class of integrals called improper integrals, okay? So we can really, infinities can show up one of two ways in our integrals. Number one is in the intervals, which are called infinite intervals. So like here, when we have integral of something going from some number to infinity, or negative infinity to some number, okay? So that's how the infinity comes into play. Or the function itself could be discontinuous, and that's how the infinity comes into play. So like here, where we have the integral of 1 over root x minus 2 from 2 to 5, where at 2 we have this discontinuity, and so that's how the infinity comes into play. Okay? So the two problems, though, both infinite integrals and discontinuous integrands, they both can be treated using the same methodology and same sort of ideology. But before we get to the treatment, we really need to understand where how this can be even possible, right? How can you add up an infinite number of finite numbers and not get infinity? Okay? So to sort of explore that, we're going to look at a case and basically compare these two integrals that look very, very similar, but are going to give us vastly different answers. So this guy over here, the integral of 1 over x from 1 to infinity, as you may know, equals infinity. It's divergent. It diverges to infinity. Whereas the integral of 1 over x squared from 1 to infinity will give us a perfectly well-defined result. In fact, it's very nice, 1. So how could these two functions that are so similar on the same interval give us such different answers? In fact, if we were to graph 1 over x and 1 over x squared, look how similar they are. This is 1 over x. 1 over x is just a little, 1 over x squared is just a little steeper. That's it. It doesn't cross the x-axis. Sorry about that. Right? So how could this happen? Well, the answer lies in their antiderivatives, not themselves. So if we were to look at their antiderivatives, though, we get entirely different results, right? The antiderivative of, let's do 1 over x first. The antiderivative of 1 over x is ln of absolute value of x, or since we only care about 0 from 1 to infinity, it's just ln of x, right? So if we were to graph ln, it would look something like this, right? This thing goes from negative infinity to infinity as x approaches infinity. Now, the endpoints that were, if you remember a fundamental theorem of calculus, it said if you have an integral of some function from some number to some other number, it's equal to its antiderivative evaluated at those two endpoints. Okay? So now that we have the antiderivative of both functions, and we will construct the antiderivative of this one very shortly, we can just compute them at their endpoints, and it'll be, their difference will be equal to the value of this integral, right? Because of the fundamental theorem of calculus. If you don't remember, make sure you look it up, because this is very closely tied to that definition. So I can just compute this integral, this function at 1 and infinity, and the difference between those two values will be the answer to my integral, right? So it's just at 1, this thing equals some number. It's actually going to be, I was thinking of the other one. At 1, it's going to equal 0, right? Ln of 1 is 0. And then at infinity, well, ln doesn't have an upper bound. As x approaches infinity, it just goes to infinity. So it's going to be infinity minus 0. Infinity. Whereas this guy's antiderivative is negative 1 over x. Okay? If I were to draw it, it'd be something like this from 1 to infinity. So at 1, it's going to be over here, negative 1, 1 and negative 1. And at infinity, it's going to be approaching 0. It's going to be infinity and 0. The difference between 0 and negative 1 is just 1. 0 minus negative 1 is 1. And that's why the answer to that one is 1, and the answer to that is infinity. Now, what did I do? I essentially integrated it, right? Computed the antiderivative, and then found the answer. But the ideology that you sort of have to, you have to wrap your mind around this idea that, look, we don't care about the functions themselves. It's their antiderivatives that are being evaluated at the two endpoints. So even though the functions themselves look very similar, their antiderivatives are not. And the endpoints of their antiderivatives are very different. In fact, this guy goes to infinity, whereas that guy goes to 0. And that's where this difference comes from, even though the structure of the two functions are very similar. So really, we can extend this result to any 1 over x to the any power, okay? And later you may know this is very closely related to the Riemann zeta function, but for now, all we need to know about this is the fact that, look, if I'm integrating 1 over x to some power, the integral will be convergent if and only if my power is greater than 1, right? Otherwise, this will be the case, okay? Again, the reason for that is the same analysis. If we have a power greater than 1, once we find the antiderivative will be vanishing as x goes to infinity. It will approach 0. But if our power is less than 1, remember the power rule stuff, we subtract 1. So if it's greater than 1, it'll still be 1 over x to something. Even if this is, if p is 1.0001, when we subtract 1, it'll be 1 over x to the 0.0001. And as x approaches infinity, this will approach 0. But if p is less than 1, then that's not going to happen. And we're going to end up with something like this. So let's go ahead and actually do what sort of do a problem that you're going to see. You're usually not going to see something this simple. What you're going to what you're going to be asked to do is compare integrals that look similar to one of these two. Okay? And the method is simple. All we're saying is, look, if I know that this guy diverges and this guy converges, what I can do is use these two benchmarks to sort of compare different integrals that look sort of similar to these guys. So, for example, if I have 1 over x squared plus 3, okay? Since the denominator of this thing is greater than x squared, the whole thing will be less than 1 over x squared, right? So this thing will be less than 1 over x squared for all values of x. That's a fact. Okay? So if I integrate it from 1 to infinity, then I should, and I know that this guy converges, then this thing, which is less than this guy, has to also converge. Same goes for this side. If I have 1 over x, I don't know, minus 1, well, this guy is greater than 1 over x because its denominator is smaller for all values of x. So if I'm integrating over the same interval as this thing, and I know this thing diverges, well, then something bigger than this has to also diverge. Okay? So that's where this comparison method comes from, and you're going to see it again when we start to do tests and integral tests and comparison tests. So let's go ahead and use this method to do something a little more complicated, okay? Namely, the integral from 1 to infinity of sine of x over x squared plus 3x minus 1, okay? So now, actually evaluating this is a pretty bad task. It's pretty nasty, but we can determine whether it converges or diverges. So if we just look at this, immediately we can just eliminate one of the components of this, and that's sine x. Why? Because sine x, as x approaches infinity, we're not concerned with how this behaves around x equals 3 or 5 or 4. We're concerned with how this thing behaves when x is 300 billion. Okay? And around then, since sine is a cyclical function, it's just doing the same thing over and over again, bouncing around from -1 to 1, -1 to 1, -1 to 1. It just doesn't concern me. It doesn't affect this thing as x gets huge. What we're trying to watch out for are things that grow without bound, because those are things that make stuff diverge. Okay? So let's look at the denominator, 1 over x squared plus 3x minus 1. Well, obviously it looks like it's, I mean, it's got the second power, so of degree 2, but it's got 3x being added to it and minus 1. If it were only the 3x, I could say, well, for all values of x, this thing is going to be bigger than 1 over x squared. I'm sorry, it's smaller than 1 over x squared because its denominator is bigger, so the whole thing is smaller than 1 over x squared. So it's going to converge. But it's got a minus 1. Do we care? No. Again, we're concerned with x's of order 300,000 billion, right? Unimaginably big numbers. So in front of 300 billion, what's a minus 1? Nothing. We can just get rid of it. We don't care. Again, this isn't rigorous, but it works, and there's a reason that it works. And if you're only tasked with if your task is to find out whether it converges or diverges, you can use these methods. Or if you're tasked with actually showing why it does or doesn't, you can use L'Hopital's law or similar methodologies to sort of get rid of these things that are bothering you but aren't actually adding anything of value to the function. Okay? So these are more so techniques of just being able to look at a function and being able to tell whether it converges or diverges just by inspection. Okay? So this guy, now obviously it converges. Why? Because 1 over x squared plus 3x is always less than 1 over x squared, and 1 over x squared converges. So this guy also has to. Okay? So this guy converges. Now let's go ahead and look at the other class of, basically the other case where infinities come into play, namely having discontinuous integrands. Okay? So we have the integral of 1 over root x minus 2 from 2 to 5. So the problem is that at 2, this thing is discontinuous, so we're not allowed to evaluate it at 2. So what we're going to do is we're going to say, okay, well, I'm just going to pretend like I'm going to get really close to 2, but not actually get to 2. Okay? So I'm going to say, I'm going to go to 2 from the positive side. Remember, I don't care what's going on the left side, on the negative side of 2. I don't care. My interval is from 2 to 5. I only care what's going on from the positive side, from the right side. Okay? And then write this integral in the same terms, just replace 2 with the r. Okay? And then I'm also going to, instead of writing 1 over root x minus 2, I'm going to write x minus 2 to the minus 1/2, just because it's easier to integrate it now. It's easier to deal with fractional exponents, where it's just adding and bringing it down, whereas this guy, I don't want to deal with it. So I make sure I'm going to write my limit every single time, or otherwise I'm going to get points taken off. And now I'm actually going to evaluate the integral. What is the antiderivative of x minus 2 to the negative 1/2? Well, add 1, so x minus 2 to the 1/2. Bring it down and invert it. 2 times x minus 2 to the 1/2, evaluated at r, and 5. Okay, so at 5, this thing is going to be, actually, I'm going to write my limit again, because I'm a good student. So I'm going to write my, I'm actually going to evaluate it right now. So I'm going to plug in 5, 2 times 3 root 2, or 2 times root 3. And then I'm going to plug in r. I'm going to get 2 times r minus 2 all to the first power, or to the 1/2, and I'm going to get 2 to the 2 times r minus 2 inside the square root. So this guy is independent of r, so I can just bring it down to root 3. And then I have to replace 2 for r. Well, that's just 2 minus 2, 0. So this is 0. So the answer is just 2 root 3. Okay? So as you can see, it's not hard. All you have to do is just replace, sort of find where the discontinuity is happening, and then replace that number with just a limit. And say, okay, I'm not going to evaluate it at 2. I'm going to evaluate it really, really close to 2. Okay? So basically, there you have it. These are improper integrals. We discussed both classes of them. And the treatment is very similar. The ideas are very similar. all you have to do is sort of detect where the discontinuity or where's the infinity coming into play and reaching in there and grabbing it out by imposing this little limit thing on it. Okay? So there you have it.